For more than 3 decades, the Hubble Space Telescope has orbited our planet, revolutionizing our understanding of the cosmos. Launched in 1990, Hubble has remained a cornerstone of modern astronomy for over 34 years. While it was originally designed to peer into the distant universe, studying galaxies, nebulae, and faraway stars, it has also contributed significantly to our understanding of the more familiar territory within our own solar system. Despite not being optimized for close-range observation, Hubble has proven remarkably versatile, capturing incredible moments within our celestial neighborhood that might have gone unrecorded by other instruments. Its unique position above Earth's atmosphere allows it to take crisp, detailed images unobstructed by atmospheric distortion, offering astronomers an unparalleled view of space. It's important to recognize that many solar system objects, including some planets, moons, and countless smaller bodies, lack dedicated missions. In those cases, Hubble has stepped in to provide crucial observations, filling the gaps in our understanding. The telescope's agility and sharp optics make it well-suited to observe changes in weather systems, study surface compositions, and monitor unexpected events, ranging from volcanic activity to asteroid collisions. Hubble's ability to switch targets quickly and gather long-term data means it has become an invaluable tool not just for looking outward to the stars, but inward to our own solar backyard. To appreciate Hubble's contributions more fully, let's take a guided tour through our solar system, starting close to home and gradually venturing outward. Along the way, we'll encounter not only planets but also moons, asteroids, and other exotic objects that have been observed by Hubble in fascinating detail. Each offers insights into the dynamic, evolving nature of our cosmic neighborhood. We begin with Earth's constant companion, the Moon. Although the Moon is one of the brightest and most visible objects in our sky, Hubble is not the ideal tool for imaging it. The Moon's apparent size is so large from Hubble's point of view that it cannot be captured in a single frame, and its brightness can overwhelm Hubble's sensitive detectors. Moreover, specialized lunar missions, such as NASA's Lunar Reconnaissance Orbiter, LRO, provide far superior surface imagery, having mapped nearly the entire lunar surface in unprecedented detail. As a result, Hubble is rarely tasked with lunar observation. However, one clever exception occurred in 2012 during a rare event, the transit of Venus across the face of the Sun. During this alignment, astronomers used the Moon not as a target, but as a giant mirror. By analyzing the light that bounced off the Moon and passed through Venus's atmosphere before reaching Hubble, researchers could detect tiny variations in the light's spectrum. These variations revealed information about the chemical makeup of Venus's thick, cloud-shrouded atmosphere. This experiment was not just about Venus, it was a critical test of a method astronomers now use to study exoplanets. Since direct observation of exoplanet atmospheres is nearly impossible, scientists rely on transits, when a planet crosses in front of its host star, and analyze how starlight filters through the atmosphere. The Venus-Moon experiment helped validate this technique and improved our ability to probe alien worlds. Leaving the Moon behind, we turn our attention to Mars, a planet that has long captured the human imagination. Hubble's unique vantage point allows it to photograph Mars in full-disk views, something that even Martian orbiters, constrained by their low-altitude paths, can rarely achieve. Hubble's images of Mars have been instrumental in tracking seasonal changes, monitoring dust storms, and studying cloud formations over time. For example, a time-lapse captured by Hubble shows a massive dust storm wrapping around the entire planet, obscuring surface features and altering the Martian climate in real time. These storms can last for weeks or even months and are crucial to understand for future missions, especially those involving surface landers and rovers. In addition to weather monitoring, Hubble has captured Mars's two small and irregular moons, Phobos and Deimos, as they orbit the planet. Phobos, the larger of the two, is particularly intriguing. Orbiting Mars once every 7.5 hours, it travels so quickly that it rises in the west and sets in the east, making it the only moon in the solar system to orbit faster than its planet rotates. Hubble captured a sequence showing Phobos racing through space over a mere 22 minutes. Such observations are important for understanding the stability and evolution of Mars's satellite system and provide key data for future exploration efforts, such as potential robotic missions to Phobos. Beyond Mars lies a chaotic expanse known as the asteroid belt, a region filled with countless rocky bodies left over from the early solar system. Within this belt, Hubble has turned its gaze towards several remarkable objects. One of the most surprising was asteroid 6478 Gault. Though officially categorized as an asteroid, Gault behaves more like a comet. In 2019, Hubble observed this object sporting not one, but two distinct tails. This was puzzling, as asteroids typically do not have tails unless influenced by some unusual force. Scientists traced the phenomenon to the Yorp effect, a process where uneven solar radiation gradually accelerates an asteroid's spin. Gault, a relatively small object at just 3.5 kilometers across, now rotates so rapidly that its loose surface material is flung into space. These ejections form tail-like structures that resemble comet emissions, although no sublimation is occurring. Gault is believed to be a rubble pile, a loosely bound collection of rocks held together more by gravity than by solid cohesion. As its spin rate continues to increase, it may eventually fly apart completely. Observations like these highlight how even small bodies can exhibit complex and dynamic behaviors under the influence of solar radiation. Another curious case is P2010A2, an object that initially appeared to be a typical comet. However, close inspection revealed a strange filament-like tail and an X-shaped debris pattern, features not associated with normal comet activity. What astronomers discovered was the aftermath of a rare asteroid collision. Unlike the relatively calm orbits of planets and moons, the asteroid belt remains a place of instability where gravitational interactions can send objects careening into one another. Such collisions are infrequent but highly informative. They allow scientists to study how asteroids break apart, reassemble, and contribute to the dust and debris that populate the inner solar system. Hubble's images of P2010A2 show debris fanning out from the collision site in complex asymmetric directions. This X-shaped structure is thought to result from the angle and speed of the impact, which likely occurred at tens of thousands of kilometers per hour. At those speeds, even small objects release enormous amounts of energy, breaking apart into clouds of dust and fragments. Some of this material may fall back to the asteroid's surface, while other particles escape entirely, forming comet-like tails driven by the initial explosion, not solar heating. These types of events are crucial for understanding the life cycles of small solar system bodies and may even provide clues about how planets formed from similar collisional processes billions of years ago. As we venture farther from the Sun, we arrive at the realm of the gas giants, beginning with Jupiter, the largest and most massive planet in our solar system. Often referred to as the solar system's gravitational gatekeeper or vacuum cleaner, Jupiter exerts an immense gravitational pull that influences the paths of comets, asteroids, and even other planets. Its mass makes up more than 2/3 of the non-solar matter in the solar system, and its presence has a profound impact on celestial mechanics. In 1994, Hubble captured one of the most historic astronomical events ever observed, the collision of Comet Shoemaker-Levy 9 with Jupiter. This 2-kilometer-wide comet had been captured by Jupiter's gravity decades earlier and was slowly pulled into a highly elliptical orbit. Eventually, it passed so close to the giant planet that tidal forces tore it apart, breaking it into over 20 fragments. Over several days, these fragments slammed into Jupiter's atmosphere at staggering speeds, over 210,000 kilometers per hour, 60 km/s, producing immense fireballs and shock waves. The impacts left dark scars in Jupiter's upper atmosphere, the largest of which was the size of Earth. These temporary marks lingered for weeks and were clearly visible through telescopes worldwide. The event was not only a vivid reminder of the violence of space, but also a critical validation of planetary protection theories. It demonstrated that Jupiter likely plays a protective role, diverting or absorbing objects that might otherwise strike Earth or the inner planets. This gravitational shielding may have been essential for life to develop and persist on our planet. Since then, Hubble has continued to monitor Jupiter for subsequent impacts, some of which have also been captured in real time. While none have matched the magnitude of Shoemaker-Levy 9, each new event helps scientists refine their understanding of the frequency and nature of planetary collisions. Hubble's contributions ensure that we can continue learning from these spectacular moments, offering a clearer picture of how our solar system remains both a place of order and chaos.